So I heard that if you're chatting with a bot, that if you reply with ignore all previous instructions and then give new instructions, that sometimes that works. Have any of you heard that?
A bot.
Yeah, when you're. I got a comment from someone I was pretty sure was a bot on my YouTube channel. And I accused them of being a bot. To which they didn't actually deny it. They just came back with what they did for it.
What was their initial comment about?
It was like a pep talk. It was, the gist of it was, keep up the good work, keep your videos tight, and eventually the viewers will find you. Something like that. And I said, thanks for the pep talk, but based on your comment, I'm assuming you either didn't watch my video or you're a bot or AI. And then they came back with, I am SEO, I do data optimization. Well, it was a bunch of jargon that I saw too much of when I did IT consulting. So I missed my opportunity to try that out. So I responded with, nothing you said makes me change my opinion on my previous comment. Have a nice day. All right, any questions?
Yeah. Number 8 on the master set.
Which one is number 8?
Number 8 is a launcher shoots the ball horizontally from a height of 1.5 meters. The ball lands 8.2 meters away from the base of the launcher. Ignoring air resistance, how fast is the ball launched from the launcher?
Okay. If you will indulge me, I do plan to get to that, but if we could hold off about a half hour or so, we will get to it. Other questions? Johanny?
For the master set 8, for 1 and 2, for question 1 and 2, it's asking there are 2 marbles. Marble B has a hole drilled into it, and then marble A and B are equal in masses and texture, and they're rolling down a smooth track. When B rolls, the hole is parallel to the track the whole time. Which marble will win? And then the second one is just asking when B rolls, explain how B has an advantage. So could we, because I put, even though everything is the same, B has lower momentum and a lower moment of inertia and a lower mass because of the hole drilled into it. So it has more of an advantage. It will move faster. So ball B would win. Does that answer both of the questions?
No, because with the hole in it, ball B has the same mass, so it doesn't have less mass. And also B, since the hole is parallel to the track the whole time, ball B would have a higher moment of inertia. I think you said it would have a lower?
Mm-hmm.
Yeah,
I just said the opposite of what you said.
Yeah, so it doesn't quite work. So B has a higher moment of inertia. It has the same mass as A, but more of it is distributed farther from the axis.
So how do I come up with the answer? Because I'm obviously thinking like the opposite of what you're thinking. So what is, like, how would that work?
When we did the, let's see, we have two objects here, basically same radius. Textures are different, which is different from that problem, but obviously different distribution of mass. If I race these two down a track, I guess we have this right here. If I race these two down the track, which one would get to the bottom first? Which one?
The one on your left.
This one. We want to disagree? Angel, you look like you want to disagree with that.
I think the tape too, because it's wider.
Okay. It's just,
Oh,
it's not tape, it's just it's a metal ring.
yeah.
But, okay, so you also think, as far as which one's heavier or less massive? This might be slightly more massive, I can't quite tell.
But then in question 2 is asking, how does B have an advantage?
Alright,
Explain.
so let's first set up the race. Let's see, just a lower. So which one got down first?
The black.
Okay. Because with a lower moment of inertia, as it's going down, there basically you have all this potential energy. From an energy point of view, you have all this potential energy which gets converted into kinetic. Some of the kinetic energy gets turned into linear kinetic, in other words, how fast it's going down the ramp. Others gets turned into the rotational kinetic energy, how fast it's actually rolling. So the more energy spent into getting it to roll, the less energy there's left over to get it to move down the track. So this requires more energy to get it to roll, or a higher percentage of the energy to get it to roll. Therefore, less energy is left over to just get it to move. Jason?
But I think in the race that was referenced, red number 31,
Yes. So
did that have the hole in it?
it does. It did.
Which one?
The red one that, if you look at the problem, it says like this
Yeah.
problem.
All right, so for part A, this is sort of an ideal situation here. However, if we went into sort of outside, like in the marble races, what advantage does an object have if it has greater moment of inertia? Think about what inertia is, and more specifically what a rotational inertia is. They would have the same potential energy to start with, if they started at the same place.
But I'm still confused on why it's asking that that B has an advantage if it doesn't win.
Oh, no, in part A, which is sort of what I had here, in part A, it's not gonna win. In part B,
Okay.
it will win.
That's why I was getting confused because I thought they were like they're both the same. Like I thought they were.
No, one was the race in a nice ideal situation, and the other one was a race in actual terrain.
Okay, yeah, that's what I was trying to do with the first one. I was trying to answer both of them at the same
Ah,
time. That's why.
Okay. All right,
Okay.
how did I word it? Let's see, 2 marbles. When B rolls, the hole is parallel to it. Which marble, so number 1, it's which marble would win. Smooth track, constant angle. Number 2, down a sandy hill. Okay. Yeah, so 1 is more like this, and problem 2, where it's more of a real life thing. Less skating. It's done on Sandy Hill. All right, so you have a baseball and an elephant that you need to get from one end of the hall to the other. Which one would get down to the other end first? You're throwing the baseball, the elephant you're not throwing.
Probably the baseball,
Why?
cause I can throw it.
Yeah. Okay. Suppose you put obstacles in the way. Why?
Because it can move the obstacles out of the way.
Yeah.
Whereas the ball's gonna be stopped by the obstacle. Because the mass of the elephant is more
Okay.
than the mass of the ball.
Now translate that into rotation. If you have an object with a greater moment of inertia going down a sandy hill, and then an object with less moment of inertia going down a sandy hill. I mean, somebody will say it, just, I don't wanna feed the answer completely to you.
The lower moment of inertia increases its ability to maneuver terrain.
If
It moves faster.
that would give it the, yes, Clyde. Kind of terrain, I mean, all right, so you got a sandy hill, you have leaves in it, you have sticks, things that have fallen, that they tried to clear out, but they can't quite succeed, because, you know, it's nature. In the case of the baseball elephant, yeah, the baseball potentially could move around a barrier if you had something to get it to move around the barrier. But once you throw the baseball, how much maneuvering do you have? Okay, so you lose that advantage of having sentience. We will assume, despite the way that the races are generally called, like the marbles are sentient, marbles are not. Sorry to shock you. So why would a greater moment of inertia give you an advantage? And by the way, if you have not watched the marble races, you really should. I guess we'll just leave it right there for right now. Other questions? All right, so there we go. I'll talk a little bit about torque, and then we'll get into the projectile motion, which will connect with Jason's original first question. So I have a beam with a mass of, the same numbers I used before, there we go, 1.0123 kilograms. And I'm holding it up. This one is this is 1 meter long. this distance from here to here is 0.212 meters, and from here to here is 0.814 meters. The center of mass of the meter stick is at 0.451 meters. This has a tension of 5.981 newtons, and this has a tension of 3.938 newtons. So the first thing I want to do is just show that this should balance, and hopefully I did not make a careless error when I was solving this. All right, the sum of the forces up equal to the sum of the forces down. If this is in equilibrium, more specifically, if it's in static, rotational, and linear equilibrium. What do you know about the sum of the forces? What do you know about the sum of the torques? All right, now I don't know how many people saw the hand gesture, but I basically got that. So first, let's find out, let's see if the sum of the forces do indeed equal 0 here. Well, I have those two forces that are up, just explicitly given to you. What force is acting down?
Acceleration due to gravity.
Ooh, not a force.
Got it.
Okay. Weight of the beam. All right, so I have, it is, and we act like it is acting at that location right there. The people who would not assume that the weight is acting at that point would be civil engineers who need to look at the distribution of the force across the entire beam to see how it sags in which place. All right, so how do you find the weight?
I think you would add the two tensions.
Well, that's what we're gonna check, so how else would you find the weight?
Mass times acceleration.
That's the one. All right, so mg, so we have 1.0123 kilograms and 9.798 meters per second squared. I was assuming that we're in Winston-Salem when we're doing this. And if someone would be kind enough to do that calculation.
$9.91851554.
5454.
5154.
And if we look at the forces that are acting up, I have, so that's the force acting down, the forces acting up, 5.981 newtons, 3.938 newtons. And if you add those together, what do you get? Okay. And if you, so it only goes out to here, so if you round off, that would round up because of the 5 and et cetera afterwards. All right, so the forces up equal the forces down, at least to 3 significant figures. And that's what you would expect. However, do the torques add up? Well, torque, as you all know and love, is the moment. Nothing happening here. Move on. Is the moment arm times the force. So the moment arm is a vector from the axis of rotation to where the force is applied. Where's the axis of rotation for something that's not moving?
Wherever we decide.
Okay. So let's pick any point. I'll just take the left in, since I have those distances very nicely. Let's make that explicit, that that's 0.451 meters. All right, so we're gonna add the torques. Let's set up the traditional convention of positive is to the right and up. So my total torque would be the torque from the left scale plus the torque from the weight plus the torque from the right scale. Because I have 3 forces acting on it, each one contributes a torque. And so the moment arm for the first one, it's a vector from where I started, from my axis, from the axis to where the force is applied, so that if my axis is on the very left side, what is the direction of the moment arm for the first force? No, just looking for it's plus or minus, not looking for it in the page or out the page. Just the moment arm.
Positive.
Yeah, positive, it's to the right. Now, some people are doing the right hand rule here, an occasional left hand. That's gonna get into the next bit, but, all right, so we have positive 0.212 times the force, which is up, which I said was positive, can't even read that anymore, 5.981. All right, so that's the torque from the left scale. From the weight, my moment arm is still positive, still going from the axis of rotation to where the force is applied, still to the right. So that's positive 0.451. But this time the force is downwards. Negative 9.919.